is your video for 11.7, the final lesson of our entire career in geometry, actually. Unless, of course, you have to see me again next year. Here we go. The concept that we're dealing with today is similar solids, so how three-dimensional objects can relate to one another. Now, two solids can be considered similar if they have the same shape and all their corresponding dimensions are proportional. So a concept that we're going to need to remember in this particular section is how to solve proportions, okay? Side note, you should always remember that any two cubes are similar because all their sides are the same, as well as the fact that any two spheres are also going to be similar. This is just that same idea as we have with circles. Here's our first example. Are the two rectangular prisms similar? If so, what is the scale factor of the first figure to the second figure? Well, the first thing that I need to do is I need to ensure that corresponding parts are proportional. So corresponding parts, I have a 3 and a 6, okay? So I'm going to create a proportion, 3, 6. I have another set of sides, 3 and 6, that are corresponding. So far, I look pretty good because 3, 6 is equal to 3, 6. And then I also have the last sides of 2 and 4, the relationship of 2 over 4. Well, I'm noticing that all of these fractions are equivalent because all of these fractions simplifies to 1/2, okay? Because they all simplify to 1/2, I know that these two figures are similar, as well as the fact that their scale factor is going to be 1/2. Okay, let's check it with our next set. On our next set, I have corresponding sides of 2 and 3, and I'm going to relate that to corresponding sides of 3 and 6. So far, I am done. Well, it's not so good. 2/3 does not equal 3, 6. Therefore, these two polyhedrons are not similar. Okay? It is now your turn. You're going to do the same thing, dealing with cylinders. Are these two cylinders similar? If so, what is the scale factor of the first figure to the second figure? Please do not be daunted by the fact that you're dealing with a radii and a height. You're still going to treat them the same. All right, you should have identified that yes, indeed, these are similar cylinders because 6/5 is equal to 12/10. Notice that we corresponded the radii as well as the heights, okay? The radii don't equal the heights, however, the proportions of these guys do equal each other, okay? All right, let's move on. How do the areas and volumes of similar solids relate? So this entire chapter has been dealing with surface area, lateral area, and volume. So let's take a look at these two similar prisms. I already recognize that they are similar. I've already given you that information, okay? The ratio of their side lengths is a ratio of 1 to 2, okay? Notice I have a side length of 2 and a side length of 4, which is why my ratio is 1 to 2. If I find their surface areas, which has already been given, the smaller guy has a surface area of 22 meters squared, and the bigger guy has a surface area of 88 meters squared. So the ratio of their surface areas would be 22 to 88, but that simplifies to 1/4. Let's take a look at their volumes. If we find the volumes of each of these figures, the smaller guy has a volume of 6 meters cubed, and the bigger guy has a volume of 48 meters cubed. 6 to 48 simplifies to 1/8. By looking at these relationships, it lends itself into analyzing what the relationship is between these ratios. Okay? If you have the ratio of their side lengths, and we call it A to B, all we need to do is square both A and B in order to find the ratio of their corresponding areas. Side note for areas, okay? This could refer to lateral area or surface area, okay? Also, if you have the ratio of their side lengths, then you can also find the ratio of their corresponding volumes, and that's just going to be A cubed to B cubed. So notice that they just step up depending upon what you're trying to find, and this also corresponds with their unit degree, okay? So notice that the ratios correspond with the degree of their unit. All right, so the square prisms at the right are similar. What is the scale factor of the smaller prism to the larger prism? When I am given volume, like I am here, I know that I am given a ratio of something cubed over something cubed, okay? That is what I am given. All right, so we're going from the smaller to the larger, so I'm going to put the smaller on top, So we have 729 on top, and we have 1,331 on the bottom. Okay, I'm going to use this relationship here in order to find out the scale factor. Now I want to get rid of cubic degrees, therefore I'm going to take the cube root of both sides of my equation. Okay, that's going to get me just A over B, and then what I need to do in my calculator is I need to take the cube root of 729 as well as the cube root of 1,331. And when I do this, when I take the cube root of both of my numbers, that gets me a ratio of 9 over 11. Therefore, this is my scale factor, and I'm going from the smaller to the larger prism. Your turn. You are also dealing with scale factor, but in yours, you are given two surface areas. So please note that you are dealing with a different type of ratio. I also want you to answer the question of, are any two square prisms similar? This might be a good idea, a good time for you to try something. Alright, so in 2A you should have found that the scale factor is a ratio of 2 to 3. Please note that in your problem you should have been using square roots, not cube roots. And to answer the question, are any two square prisms similar? No, the bases are similar. However, the heights may not be the same ratio as the edges of the bases. Alright, this is going to be basically the rest of the chapter, but we just need to apply our knowledge in a few different ways. So the lateral areas of two similar paint cans are 1,019 centimeters squared and 425 centimeters squared. The volume of the smaller can is 1,157 centimeters cubed. What is the volume of the larger can? Alright, well, what I can do is I can recognize that because I have both lateral areas, I can find the scale factor. Okay? Because I'm given lateral area, I know that I'm given a ratio of A squared over B squared. And I'm going to set that equal to my lateral area. So I'm going to do 1,019 on top and 425 on the bottom. So I'm going to deal with the larger paint can over the smaller paint can. Alright, just like you did in your Got It, I'm going to take the square root of both sides of my equation, giving me a scale factor of A over B. That's going to be equal to the square root of 1,019 over the square root of 425. Okay? Alright, I'm going to preserve this in my calculator. I'm not going to type it in now. I'm going to use this. Okay? And now I'm going to set up a ratio using my volumes. Okay? A cubed over B cubed is the ratio of two similar solids volumes. Okay? Alright, so what I have is I need to set up a ratio, and I want you to remember that it is important how you set the proportion. Because we are dealing with the larger paint can over the smaller paint can, we need to remain consistent throughout. Okay? Alright, so volume of the large over the volume of the small, that's going to be equal to, my value for A I found is the square root of 1,019. And I'm going to cube that because that is what we do when dealing with the ratio of volumes. My value for B is the square root of 425, and once again I'm going to cube that. I'm going to take this entire expression into my calculator. Please make sure you are doing this carefully. Please make sure you get the same answer as I do. And the last thing I need to do is I need to recognize that I already have my volume for my small, so I'm going to simply plug that in. My volume for my small was 1,057. So all I need to do is multiply both sides by 1,057. And whatever that number is that you got in your calculator for this red quantity, I'm going to multiply that by 1,157. Okay? So this entire quantity, I type in, if I have not done so already, and I find that the volume for the large is a sizable number. It is 4,295.47. So I'm going to say approximately, because it didn't tell me what to round to, 4,295.5. My unit of measure here, we are dealing with centimeters cubed. Okay? Alright, so please make sure you're getting really good at finding those buttons on your calculator. Kind of important here. Here's the volume of two more similar solids, and you have the surface area of the larger. In your problem, you are finding the surface area. So please recognize what information you are given. All right, because you were given volume in your problem, you are going to need to take the cube root in order to find your values for A and B, okay? And then when you plug yours in, you're going to have to square your cube root and then once again multiply by the volume, the surface area that was given. And you should have found an approximate surface area of 160 meters squared. Last problem of the entire course of geometry. How incredibly exciting. A bottle that is 10 inches high holds 34 ounces of milk. The sandwich shop shown at the right is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could that building hold? Interesting. All right, so things you need to think about is recognizing how capacity is relating to volume, okay? Since the capacities in similar objects are proportional to their volumes, the ratio of their capacity is also going to be equal to their volumes. So that's what this question is really asking me for, dealing with that volume component, okay? Because I have the height for the bottle as well as the height for the building, I can find the ratio of their side lengths, aka I can find their scale factor. 10 to 480 is going to simplify to a scale factor of 1 to 48. So what I've been given here is my ratio of A to B, okay? That is the piece that I need to utilize, okay? Because I have a ratio of A to B, that means I can find my ratio of A cubed to B cubed, which is the volume ratio. So all I need to do is cube both 1 and 48, okay? So when I cube 1, I get 1. When I cube 48, it's a sizable number. It's 110,592, okay? So there's the ratio of my volumes, okay? Now I just need to remember how to set my proportion and set up the corresponding solids. The one in the numerator represented my smaller bottle, and my smaller bottle holds 34 ounces of milk. What I don't know is what that sizable building is going to hold, and so then all I need to do is solve my proportion, okay? So I'm going to multiply the x onto this side. I'm going to multiply the 110,592 onto the other side. 1 times x is just x. And when I type into my calculator 34 times 110,592, we get 3,760,128. And we're going to give that a unit of measure of ounces. Now, this question told me to round, and it told me to round to the nearest 1,000 ounces. So 1,000 mark is right here. So this is going to round to being 3,760,000 ounces of milk. Okay, I gotta give myself the rest of my zeros here. Okay, and I'm just gonna throw commas in there because it just looks a little bit nicer. All right, your turn. The last guy at our geometry. I'm getting sentimental here. All right, so in your problem, you should have found the ratio of the volumes, and the ratio of the volumes, it would be a ratio of 1 cubed to 3 cubed, which just gets you 1 to 27, okay? Think about how that was slyly given. It was given because the weight of each dimension is 3 times as large, so you just have a ratio of 1 to 3, okay? And then you just set up your proportion of 1 to 27 equals 0.15 over x, solve for x, and ta-da, you are officially done with geometry until you take your final.